I'm going to be revisiting some unsupervised pre-training stuff today. This is reconstruction-based methods as opposed to the contrastive methods that we looked at on Monday. All right, so the plan for today, we're going to do a little recap on what Chelsea talked about on Monday. So we're going to talk about the unsupervised learning problem setup and just go over contrastive learning briefly. And then the meat of the lecture is going to be about reconstruction-based unsupervised pre-training. So the main difference here is that we're not learning by comparing multiple examples. We're sort of learning one example at a time by just trying to compute a representation and then reconstruct the example. And we're going to talk about a couple different instantiations of this idea. Some of them you've probably heard of before, some of these big, fancy, hopefully not scary models. And a lot of this content is going to be stuff that's homework 3 is on, so it behooves you to pay attention. And you're the people who came, so you're already ahead of the curve. And if you pay attention, you'll be even farther ahead of the curve. So hopefully by the end of the lecture, you'll have some familiarity with some of these now pretty widely used methods for unsupervised pre-training and some of the ways that we can then fine-tune these models once we've pre-trained them, and ideally be ready to breeze through homework 3. All right, so just to start this recap, so as Chelsea said on Monday, in unsupervised learning, we have some large unlabeled data set, ideally a diverse unlabeled data set. We do this first gray arrow, which is unsupervised pre-training, and this gives us our pre-trained model. And then once we have our pre-trained model, we usually use some often small data set for fine-tuning to specialize this model to a particular task. And the goal is to get sort of a good predictive model for this particular task. And after that, we talked quite a bit about contrastive learning on Monday. So the basic idea here is that examples that are similar, in some sense, should have similar representations. And so this could be examples that have the same class label. This could be examples that just come from nearby regions of an image if we don't have class labels. It could be augmented versions of the same example by flipping or cropping or adding noise. Or if we have sort of temporally structured data like videos, we can take video frames that come near each other in time to get sort of positive pairs. Another thing that we talked about is it's not good enough to just take things that are similar and push their representations together, because then we end up with this degeneracy where everything gets the same representation. So we actually need to contrast things too, and that's how we get this wonderful name, contrastive learning. And sort of the most straightforward implementation of this is this triplet loss. So here we have a triplet because we have kind of our anchor example, and then we have a positive example, which we say is sort of the similar one, and then the negative example, which is different. We push together the similar ones, and we pull apart the negative ones. And then you can generalize this to have more than one negative. So this is this sort of n-way classification loss, which is used in the SimClear paper that you might remember, which is also known as the NT-XN, or normalized temperature scaled cross entropy loss, which is really an awesome name. One minor correction from Monday is there were some questions about whether or not the similarity score for the positive pair shows up in the numerator and the denominator, and it does. So in the SimClear loss, we have the similarity score for the positive pair in both the numerator and the denominator. And the reason that's useful is since we have this positive score in the denominator and the numerator, we know that this fraction is going to be between 0 and 1. And so we can sort of interpret this as a classification probability. And so really we can kind of just think about this contrastive objective as like training a classifier with a representation. So it makes it a little easier to think about the loss and what it's doing. All right, how do we feel? Yeah, I love the enthusiasm. Keep bringing the energy, folks. Okay, so now let's talk about some reconstruction-based unsupervised objectives. So again, the main difference between these methods and the contrastive methods are we're not comparing and contrasting multiple examples. We're sort of doing this one example at a time, which makes things a little easier. And the simple intuition for these methods is that a good representation of our data is one that lets us reconstruct it. So if we have some image of this lovely little dog, we might pass it through our encoder to get a representation. And ideally, if we have a good representation, we should be able to decode this representation back into our original input, and ideally with a decoder that's not absolutely massive. It should be sort of a reasonable size decoder. And sort of the bonus of this type of setup is that we don't have to worry about things like sampling negatives or using large batch sizes, because again, this objective is purely defined on just a single training example. And so we don't have this sort of more complicated relationship between multiple examples in a batch to worry about. Okay, so that gives you a little bit of a flavor of what we're talking about, and we can make it a little more concrete. So we have this intuition that a good representation is what lets us reconstruct the input. So how do we actually train the thing? Well, we really just define some loss function that tells us how close our reconstruction is to the original input. So for images, we might use just L2 or squared L2 distance. And then we train this whole thing end to end. So we train the encoder and the decoder end to end. And hopefully by the end, our encoder gives us representations that are useful. So that's kind of a neat story. But I'm curious if people have any creeping suspicions on what can go wrong in this situation. If you've ever trained a VAE, you might know the answer. Everything. It is included under everything. Yes?
So if R is larger than X, then the encoder will just memorize the input.
Boom. You saw my slides, didn't you? Very impressive. So yeah, so I mean, one way to think about this is, according to this loss function we've written down, would the identity function be a good encoder or decoder? That's not actually totally rhetorical. I'm curious if it would be. So the answer is yes, it would be. Because if we have the identity function as an encoder, R is just X. And if the decoder is the identity function, X hat is X, so our loss is 0. And that's like a great loss function, or a great encoder and decoder for this loss, but it's not really useful. So the question is, how do we fix this? And there are a lot of different ways to fix this, but we're going to focus on one common one that people use. So if R is basically unconstrained, if it's just as high dimensional as our input, then there's no reason the encoder can't just copy the input into the representation, and then the decoder just copies that representation to be its prediction. And this is not really useful. We're not learning anything meaningful. And so the key idea that people use to kind of get around this issue is adding some sort of a bottleneck on our representation. So the most common, maybe most intuitive type is just make it lower dimensional. So we might have an image that's like 100 by 100 pixels, and our representation might only be 64 dimensions. So intuitively, it's much harder to just copy the whole image into this low-dimensional space. And so the hope is that these latent dimensions in our representation will actually be forced to represent some high-level concepts that are more kind of efficient in storing information than just memorizing 1 pixel at a time. Okay, so let's say we train this model now. So we have this encoder that compresses our input into some more compact, in some sense, representation. How do we actually do the few-shot learning part? Well, we'll throw away our decoder, and we can just initialize a prediction head on top of this representation. So really what we've just learned is a feature extractor of our data, and now we'll just treat this as a normal machine learning problem. We can fit some sort of prediction head to these representations instead of the raw images. This could be an MLP, or it could just be like an SVM or whatever. And we'll train it to make classification scores. So here, if we're doing like 5-way classification, we just have a classifier now. And the simplest recipe here is we'll freeze the encoder and just fine-tune this prediction head, or just fit the prediction head. Okay, so this is the basic autoencoder or bottlenecked autoencoder setup, which is kind of you can maybe think of like the simplest thing that kind of works. And the pros here are that it is very simple. It's very general. You can kind of do this for pretty much any sort of data, because all you need to do is pick this distance function, which you can usually come up with some sort of distance function for most data modalities. You also have this advantage compared to contrastive learning that we don't need to select these positive and negative pairs. And this is often the sort of most difficult part of the contrastive learning setup. And so it's really nice to get rid of that. But the major downsides here, in particular, is that we have to design this bottlenecking mechanism. And turns out this is really hard to do well. So you can use this sort of low-dimensional bottleneck. In practice, this doesn't really give you that good of representations, even if you make it relatively low-dimensional. And you might wonder, well, why is that? A lot of this is known mostly just empirically by training them, but what you end up with is still sort of representations that mostly memorize the images and don't actually encode sort of any sort of high-level or interpretable concepts that are likely to generalize well beyond just reconstructing this exact image. And you really do kind of end up with representations that just encode the specific details needed to minimize the reconstruction loss, but not really anything that is easily adaptable to new tasks. And so what ends up happening a lot of the time is R is more like a hash of your input than a sort of conceptual summary. And if you think about, for example, using like the gzip representation of an image as its representation for fine-tuning, like that's not going to be a very informative representation, even though it's going to be smaller than the original image. And so just compressing is not, at least in this sense of dimensionality, is not good enough to actually force our encoder to squeeze out sort of useful, reusable features. So how do we encourage the encoder to extract these high-level reusable features? And one strategy that people use is just other types of bottlenecks. So we can bottleneck our representation in many ways. We can use information bottlenecks that essentially add noise to the representation. We can use sparsity bottlenecks that constrain the number of dimensions that can be non-zero. We can also use capacity bottlenecks to force the decoder to be relatively weak so that the representation needs to be sort of easy to decode. But the strategy that actually is most common in practice is to worry less about designing a bottleneck and just make the task a little bit more difficult to force the encoder to learn something a little less trivial. And that's going to take us to our next section on masked autoencoders, which is sort of a class of models that encompasses a lot of the large pre-trained models that we have these days that we use in practice. How are we doing so far? Any questions? Is everyone having fun, though?
Yes.
Is having fun? Oh,
Sorry.
If the compile representation of the autoencoder is more like a cache, does it mean you can somehow extract the information about the samples that went into the autoencoder? Just by taking a look at the encoding and decoding part.
yeah, so in a sense you can. So it depends on the exact model and the capacity and the training data. But in the same way that you can, hash functions are generally difficult to invert, but if they're imperfect, you can invert them. A lot of the times, yeah, you can not only just decode a particular representation back into its image, but you can kind of fiddle with these models in a way that lets you extract multiple examples from the training distribution, which can pose sort of a privacy risk. Does that, great.
Yes.
So with respect to the few-shot performance of these models, since the model is kind of just memorizing details from the original image, like if you just slap a deeper passive dictation on top of that, would you result in better?
Yeah, so I mean, if you have, I guess the question is, if the representations aren't that great, like, can we sort of get around that by just making our predictor higher capacity? And we definitely can if we have a lot of data that we're able to fine tune on. But the idea is, in the best case setting, we're going to learn representations that let us perform well on our downstream tasks with really simple predictors, right? Because the simple predictors are the ones that we can fit with only a little bit of data that are very difficult to sort of overfit with. And so if we need to do this sort of thing, that sort of means like our objective's not working very well, because ultimately it just means we're not going to be able to do few-shot learning as well, because we'll need a lot of data to fine tune with. Yeah.
To make the representation more conceptual, can we go back to art contrastive thinking and say that instead of reconstructing the exact image, don't reconstruct the exact image, construct an image with a similar concept, let's say positive cues, and then maybe maximize the loss which has negative cues and don't reconstruct those. So can we do that kind of thing?
Yeah, so I mean, you could imagine sort of like a cross encoder where instead of reconstructing X, you reconstruct XPOS. Yeah, so there's not a specific paper I'm thinking of that's extensively evaluated this sort of thing, but sort of colloquially, yeah, you can do that. I'm not sure how it directly compares to stuff like BERT or any of these models here. But in a way, that sort of is what masked autoencoders do. They in a sense, they do come up with these positive pairs, and then just hang on, all right? But if you're still wondering that at the end, come grab me. All right, so we want to go beyond this bottlenecked approach to the autoencoders because designing a good bottleneck that actually forces our encoder to give us good features is really quite tricky. And so the common solution people use now is called masked autoencoders. And the issue that this sort of gets around is our regular autoencoders are really trying to predict X from X. and this is sort of a degenerate task. And so we add this bottleneck to try to avoid our degenerate solutions, but maybe the task is just too easy, and the easiest way to solve the issue is not to design a really fancy or really perfect bottleneck, but just make the task a little bit harder. And so that's sort of the approach that we're taking with masked autoencoders, where we no longer predict X from X. Instead, we just mask out a little bit of the input, and we try to reconstruct the other part of the input. And so in this sense, going back to your question earlier, we sort of are doing this in that now X and Y are not the same. They're sort of like this positive pair that's generated by literally just like partitioning the input into pieces. And this does work really well. So you're just like 5 years too late. But otherwise, that would have been like a brilliant research idea. So that's sort of the gist of masked autoencoders. And this is, even though this is a relatively small departure from the autoencoders we already saw, it's a really, really powerful framework for representation learning that is pretty widely applicable. Okay, so let's go over kind of the general recipe for how masked autoencoders get trained in practice. So again, just like when we're training a regular autoencoder, we need to pick some sort of distance function that tells us how good our reconstructions are given the original input. So this part is the same. And then for a training batch of examples, for each example, what we're going to do first is we're going to sample what we're going to define, which is a masking function. So we're going to take that example, and we're going to generate x tilde, which is sort of the masked out version of that example, and then y, which is like usually just going to be everything else. So typically, x tilde and y are just going to be disjoint subregions of the input. So in the image example, it's literally like partitioning the image, and one part is x tilde, the other part is y. And then we're going to make a prediction with our model, f theta, that gets not x, but x tilde as input. And then we'll compute our loss. So our loss is going to be between y, which is the sort of held out part of the input, and y hat, which is what our model thought the held out part of our input is. In some cases, the target might just be all of x, not just the held out part, but this is a relatively minor detail that doesn't make a huge difference in practice. And so these highlighted parts are basically our design choices or our control knobs. And two of them are pretty much the same as regular autoencoders, the model and the loss function. It's really just this masking function that we are now able to define, which gives us sort of one more knob to turn. And so again, as an example, in the case of an image, we'll split it up into two subregions. And our model might be a convnet or a transformer, which we'll talk about a little later. And our distance function might just be L2 distance. In the case of language or one-dimensional sequences, we might just mask out a couple of the words or the tokens in our sequence, and that's sort of our noisy input, and our targets are just the words that were there, or the original data there. Here, often, and pretty much all the time now, the model that we use is a transformer, such as BERT, which again we'll talk about soon. And the loss function or the distance function here is usually KL divergence or cross entropy between the model's predicted distribution of what it thinks the missing words were and what they actually were. Okay, so probably to talk about a couple of specific instantiations of this framework, probably the most famous one is BERT, which maybe you've heard about, which is this large transformer model that's pre-trained on a huge amount of text that's really good for fine-tuning on new, usually classification tasks. And basically, BERT gets as input 2 sentences, but that's sort of a detail of BERT training. It computes representations of the sentences, and then it predicts basically the missing words in both of those sentences. And it just does this task for many, many TPU hours, and then you get out a good model at the end. So let's look at this in a little more detail. So again, we might have this text input, and here, again, as sort of just a quirk of BERT, we use 2 sentences instead of just 1 for training, but it's not hugely important. And so we apply our masking function, which gives us our masked out version of that input. And I've just annotated the time step in the sequence here that hopefully will make things a little easier to see what's going on. And so I've randomly sampled 3 of the time steps to mask out. And I'm going to define my targets, which are just the original words there. And then we stick this entire sequence with the mask tokens through BERT, and that gives us a prediction for every time step in the sequence of what the word is likely to be, a probability distribution over all words of what it thinks the word is there. That probability distribution isn't very interesting except for the time steps where we masked out the word, because for all the other time steps we know what the word is, so we just compute our loss on those masked out time steps. And this gives us basically 3 distributions that are actually needed for training, which is the model's distribution for time step 2, for time step 6, and time step 9. And our loss function here, again, is going to be KL divergence. And this is going to work out to be the cross entropy between the sort of one-hot distribution that is our actual labels here, so basically a 1 on Biden and a 0 for everything else, and the distribution that our model predicted for each of those time steps. So what that works out to be is the negative log likelihood of Biden on this distribution for time step 2, the negative log likelihood of president for this distribution at time step 6, and the negative log likelihood of was at this time step 9. And we just sum those, or really average often in practice. And this is our loss for training. And then we just optimize this end to end, and we are happy. Just a couple of details about the way that BERT does masking, just for completeness. BERT masks out 15% of the time steps at random, just uniformly. And of these 15%, 80% of them get replaced by literally the mask token that I've used here, and the other 20% actually get replaced with just a random word instead of a mask token. And I'm curious if you just think for a moment why we might want to use a mixture of mask tokens and random tokens instead of just replacing it with a mask token all the time, if you think about how we're ultimately going to use this model once we've pre-trained it. Yeah?
You don't want to constrain your model to only get sentences that you see. So like you're adding randomness so that when it's deployed, you can handle new sequences.
Yeah, so you definitely don't want to sort of overfit to the types of sentences that you see during training, but it's sort of a specific type of sentence we're only seeing that we would only be seeing during training that we want to avoid, and that's what I'm trying to get at.
You want to also be able to correct the text.
Right. So we, in other words, we also want to have good representations of words that are not mask tokens. Right. So in a sense, during training, if we replace a word with a random word, and we ask our model to tell us what the original word was there, now our model, in addition to just filling in mask tokens, is also basically solving this task of, for every word in the sequence, assume the word that you see here is not what was actually there in the original text. What do you think the word would have been? And so now we have a model that not only gives us good representations of words that are masked out, but every word in the sentence. And that's important because at fine-tuning time, right, we're going to be getting sentences that have no mask tokens in them. We're just going to be shoving like real data into the model. And we don't want to be overfit, like you were saying, to only the data we see in training, which always has mask tokens in it. So that's sort of the motivation for why we sometimes actually just mix in a random word. Yeah?
So when predicting the identity of one mask token, can it see the identity of the other mask tokens?
No. Yeah, and that's for computational reasons. I mean, you could only mask one token at a time, but then you're sort of using only a very small amount of your sequence for training at every time step, and you have to make your batch very big. And the thing that makes that difficult is now you basically need to tune this percentage of the input that you're masking, right? If you don't mask enough, then you're not really like learning very quickly because you're only predicting one word at a time. But if you mask too much, now the task is too hard because you can only see like a couple words. And there's like a lot of blood has been spilled like trying to figure out like the right way to sort of do that masking. And as a perfect segue to this final point is, it is possible that we can do better than just picking random time steps. And two common ways people do this are they mask out longer spans of text at a time, so not just like a single word here and a single word there, and also do what we call salient span masking. So looking for kind of information-dense parts of the sequence or the image and masking those out instead of just like masking out random words like was or on or something. And in certain settings, these can make a huge difference in how good your pre-trained model is. We have 3 questions. I think I saw you, and then you, and then you.
Has there been any work on looking at how similar the random tokens are versus, like, how similar the random tokens are to the ground truth tokens, and how that might affect BERT training outcomes? You want it to be, you can make it to be more difficult by making it like somehow semantically similar.
Right.
Exactly the same.
Yeah, it's a good question. I'm not aware of actually ablating the criterion for how you pick a random token. As far as I know, BERT just samples uniformly from the entire vocabulary. But it would be interesting to see if you pick synonyms, basically, is that harder? Yeah, that's a good question. Someone back here.
I'm sorry, I don't understand like how the random token thing process. Like instead of asking it, you fit in a random word and then you click word to figure out what the random word was.
What the original word was. Yeah. Yes.
If you could repeat the question for the recording.
Oh, yeah, sure. So the last question was just that, what do you actually do when you put in a random word? What are you predicting? And the idea is you replace, like, for position 9, you replace was with, like, apple, and then the model has to predict what word originally was there.
When you say we're selecting for information dense spans, is this like what we're saying is we're looking for something with like high entropy, or how do we
Yeah, it's a good question. So the question was, when I say information dense spans, what does that actually mean? There are a lot of heuristics people use, but oftentimes people will just take another model that has been trained to recognize essentially like dates and names, and just like pick out all the dates and names, which often end up being high entropy portions of the text, right? If you say, my name is blank, it's gonna be extremely high entropy distribution, right? Because it could just be anything. So essentially that. But it's difficult to actually compute the entropy itself, so we use this proxy, which is classifying the type of word it is. Yeah.
Why don't we use a random mask for all tokens? Like instead of the masking, just use a random token maybe.
That's a good question. I guess I would suspect that using random tokens are a little bit more damaging than mask tokens, because for a mask token, the model sort of knows it can ignore that time step. There's no information there. Whereas if you replace everything with a random token, the model sort of now has to solve two tasks. First, it has to figure out which are the time steps that have like real tokens and which are the ones that don't have real tokens. And then once it has figured that out, then it has to try to figure out what was the original token for those time steps where they are sort of determined to be false. So I don't know, that's just my one potential guess, but it seems like it could just be harder, but it's a good question. Yeah.
Is the loss computed on all the tokens?
So for BERT, we just compute the loss on the masked out tokens. Because the... Oh, no, I'm sorry, including the random tokens. So yeah, the loss is just computed on tokens that are perturbed, so masked or replaced with a random token. But the tokens that are not changed, we don't compute a loss for.
What if BERT tries to change the tokens which weren't supposed to be changed?
We don't compute a loss for those tokens at all, so it doesn't matter. But intuitively what should happen is, since we are replacing some of the tokens with random words, BERT sort of should be acting as if like every word might have been replaced with a random word, and so it should be giving you a representation at every time step that is useful for predicting kind of the likely words that would have gone there.
So would there be like adversarial tokens which could like completely mess up the whole training?
Absolutely, they're pretty rare, but there are people who basically use BERT to come up with adversarial things to mask out to like train another model like BERT. I'm going to move on just because we have a lot of content, but I love the questions, I really do. Okay, so zooming back out from BERT, I hope that was useful to see that in a little more detail. But although BERT is the most famous, this sort of masked pre-training kind of approach is not a language-specific phenomenon, and especially recently, people found that this works really, really well for learning representations of images too, and also with transformers. So it's a very, very similar kind of learning setup. So here for an image, what we do is we chop the image up into a sequence, essentially. So we turn the image into a grid of like sub-regions or patches. We mask out, in this case, instead of 15%, we mask out 75%, which gives you some sense of like the way that information is spread out, or how information dense like the signals are in these two cases, which is sort of interesting. But first we just mask out tokens the exact same way we do in language, just a different percent. And then we compute the representations, in this case of only the unmasked patches. So we flatten out that sequence of all the patches that didn't get masked out. We stick them through our encoder. We get a representation of all of those. And then we insert placeholder patches into all the locations that were masked out. So now we have sort of the same shape as our original image. And in the places that weren't masked, we have our model's representation. And in the places that were masked, we just have placeholder tokens. And then we run this through a decoder to get a prediction of what the rest of the image looked like. And so at fine-tuning time, we just throw away the decoder. We just use the output of the encoder, but with the whole image. And this is really, really a powerful learning setup as well. And actually, this sort of masked autoencoder pre-training can give state-of-the-art few-shot image classification performance, and actually can do better than supervised pre-training. So if you do this procedure on ImageNet and then fine-tune on ImageNet with labels, you can actually do better than if you just trained on ImageNet with labels from the get-go. So in a sense, you're sort of extracting even more information from your training data set by doing this procedure and then fine-tuning with labels than if you just train with all the labels to start. So that's pretty cool. But in addition to that, one thing I think that's interesting is to compare with contrastive learning. So this is a really, I think, informative figure to get a sense of maybe some of the strengths and weaknesses of masked autoencoders versus contrastive learning. And the interesting regime, I think, is right here. So here we have MAE, which is this masked autoencoder model for images. And then MoCo is this momentum contrastive learning method, sort of V3, but whatever. And what's really interesting is that if we don't do any fine-tuning and we just fit, we freeze the pre-trained model and we just fit a linear head on top of the frozen model's representations, contrastive learning works significantly better than the masked autoencoder. So it's a difference of a little more than 4%. But if you actually fine-tune some of the model itself, it seems that the masked autoencoder pre-trained models fine-tune better than the contrastive pre-trained models. And so it's almost like a little bit of a trade-off of representation quality of the frozen pre-trained model versus like fine-tunability. So it's not clear that it's actually a trade-off, but it seems like for these two classes of methods, at least right now, the contrastive models give you slightly better representations, but the masked models maybe fine-tune a little better. So if you have like only a tiny bit of fine-tuning data, maybe the contrastive models are better because you don't have enough data to like fine-tune a lot of the model. But if you have a decent amount of fine-tuning data, which often we have more than like 30 examples and the hundreds of examples, the masked methods can work really well. So now we've talked a lot about transformers, and I should say that masked autoencoders work really well, and they have gotten a lot of attention. But sort of one of the things I think that has been the engine of a lot of that progress is the transformer architecture, because to do this sort of mask completion task requires a high-capacity model that you can scale. And in order to apply this recipe across data modalities, it's nice if you have some architecture that's not really modality specific. And transformers give you that. So transformers are this sort of general purpose architecture that you can pretty much just like directly point at language or images or molecules or like sequences of states and actions and reinforcement learning, and you don't really need to change the architecture. And so it makes it really easy to kind of transport this masked representation learning approach to new modalities. So I think it's important that we spend a little time just looking at transformers. Some of you might be familiar with it already, but hopefully you'll learn something. So, okay, what is a transformer? So we got a little bit of a peek in the previous slides. Yeah?
Can you go back a couple of slides? Any intuition behind why contrastive learning doesn't perform as well as masked autoencoders for fine-tuning?
Let me think about that. No. I don't have a concise answer for why I would expect this to be the case. I guess one way, and so that means my short answer is I don't have an answer I'm very confident in. If I had to totally hazard a guess, I guess you could say that the pre-training objective for contrastive learning is a little bit more like just doing classification, like we saw on that early slide, right? Like we're basically coming up with a classification score for the positive pair compared to other pairs, and so it's almost like you're pre-training like in a pseudo-supervised way. So it kind of makes sense that if your downstream task is to do image classification, maybe pre-training this way is going to work pretty well without changing the model at all. Whereas like the masked pre-training approaches is a little more different than classification, but maybe you're extracting more signal from the data. And so if you're able to fine-tune the model, it'll work better. But because the pre-training objective is a little different than your downstream task, it's not necessarily going to work as well with like no fine-tuning at all. That's the best I can give you. Oh gosh, sorry. Yeah, the question was, do we have any intuition for why contrastive methods might give us better representations but not fine-tune as well? And the TLDR was that maybe the contrastive objective is a little closer to doing classification based on the derivation we saw before. And so maybe kind of makes sense that without any fine-tuning, they do better at classification. Okay, so transformers. This is a nice figure from the vision transformer paper that I thought is a good, at least 20,000 foot view of the inputs and outputs of a transformer. So we haven't cracked into the main meat of it yet, but to see sort of what's going in, coming out of the model, transformers operate on sequences of data. And sequence in the very general sense. So this can be a sequence of words, it can be a sequence of here image patches, it could be a sequence of like bonds in a molecule, it can be kind of whatever you want. And so the way a transformer works is we somehow convert our data into a one-dimensional sequence. We convert these into a sequence of embeddings. So in the case of an image patch, we just have like a linear transformation that takes like our, whatever 16 by 16 grid of pixels and projects it into some usually like something like 768 or 1024 dimensional embedding space. So now we have this sequence of image patch embeddings. And then before we stick this into our actual transformer encoder, we do one extra thing which is really important. Well, sort of two. First, we concatenate what we call a class token in the beginning of the sequence. And this is just because at the end, when we actually want to make a classification score, we need to pick one of these representations to actually like stick in our final predictor MLP. And so we just have a special token in the beginning for that. But the really important thing is we have this thing that we call the position embedding. So we get our embedding for each image patch here, but we concatenate this like number, which really in practice isn't literally a number, but it's an embedding that is specific to each like literal position in the sequence. And this actually turns out to be really, really important because the transformer architecture itself doesn't discriminate between locations in the sequence. So it's just giving you an output that's a function of like the set of things you put into it. And so if you don't add something to tell the model that this is the embedding at position 1 and this is the embedding at position 2, you'll end up with a model that's sort of totally permutation invariant of your input. So if you totally scrambled like the patches in the image, you'd get the same output, and like that's not good. We want our model to be able to reason about the relative position of things. Okay, so what's inside this transformer encoder? The transformer encoder has a few main pieces that we'll dig into in more detail in the next slide. But at a high level, we basically have this fundamental block that we just apply over and over and over. So we'll have something like 5 or 10 or up to like 100 of these blocks that we apply in a row. And then we just take the output of the final block. And inside each one of those, what do? Well, first we have a normalization step where we just take every embedding in our sequence and we normalize it separately. So every embedding should have 0 mean and standard deviation 1. Then we do what we call multi-head attention, which is basically the only step in this whole process where the embeddings at like time step 1 and another time step will interact with each other. So this is where all of the inter-time step interaction occurs, and we'll go into the math of what exactly is happening later. We have a residual connection that wraps around both of these. And then we have another normalization step, and then we apply an MLP just separately to every time step. So again, there's no communication between the embeddings at different time steps. It's just a sort of weight-tied MLP. And then we have another residual connection that skips both of these. And then we have 12 or 24 of these blocks that we train end-to-end. So that's sort of the high-level picture of the mechanism in a transformer. And again, this multi-head attention is the only time we're reasoning across time steps. And it does so in a totally sort of order-independent way. And another thing that's worth noting is that really the only difference between transformers for different modalities, again, is this initial embedding step. So if you want to apply a transformer to your new type of data, whether it's language or code or molecules or images or 3D point clouds or whatever, all you need to do is figure out how to take my original data, which is like the raw data, and turn it into some sequence, and then you stuff it in the transformer. And usually you'll get something reasonable. There are definitely better and worse ways to do that, so I don't want to make it seem like a trivial point, but it is pretty much the only decision you need to make. Okay, so let's look at things in a little bit more detail. And this is one of the denser parts of the lecture, so feel free to ask questions if I've not explained anything adequately. But here, let's look at a language example just to not get too focused on one modality or another. So we get some input sequence. In this case, it's a sequence of words, and we have T elements in this input sequence, where here T is 6. And the first step that we're going to do is for language, we're going to do a tokenization step. And this is needed to basically convert our words into indices. because that's how we're ultimately going to convert them into vectors. So we have literally a big mapping that we store, that we fit using like a large corpus of text, and every word, or really in practice like sub-word sequence of letters, just gets assigned some number. So that's sort of the first step here. And then the second step is to do this embedding lookup, where every index, every token index, has its own learned vector. And this is how we're going to get our initial input sequence to our transformer. So every word gets a number, and then we just look at the row in our big embedding matrix at, corresponding to each of these token indices, and that's sort of our initial embedding. The only asterisk there is we add a positional embedding, like we said before, to be able to know that the word Joe came first in the sequence, not 10th in the sequence. So this is sort of that first step outside of the gray box on this last slide. This is sort of preparing our initial embeddings to then put into our many transformer blocks. And this is how we do this in the language setting. All right, so then let's get to the gray box. That's what we're all here for. So again, this is just one transformer block. And in practice, we're going to have many of these in sequence, all with different parameters that we learn. And the first thing that we do is we're going to normalize all of these vectors in our sequence independently. So each of these vectors is going to have mean 0 and unit standard deviation. And so again, we have this chunk now of t by d, where our sequence length is t, and d is the actual embedding dimension, or the hidden state dimension of our model. Then we have this self-attention step, which is sort of where the magic happens, so to speak, where we will compute this self-attention matrix, which essentially tells us how related or how similar the token at one location is to a token at another location. And this is kind of what tells us like how we should be propagating information between time steps. And this is sort of hypothesized to be what makes transformers really powerful, is that it can do this explicit sort of point-to-point reasoning instead of for an RNN, where if you have information here that's relevant to something much later in the sequence, you have to kind of recognize that here and then remember it as you process all of the tokens in between. The difference is with the transformer, I am directly comparing each token to every other token, so I don't have to do that. Okay, so how does that work? Well, we compute a new set of representations, A, which is the same shape as the input representations, but it has this particular form, which is maybe a little bit like, what the hell at first, but we'll go through it one step at a time. So there are really two main pieces. So this A, again, is the output of the self-attention step. And the two main pieces are what we'll call the self-attention matrix and the value matrix. So the self-attention matrix is this thing that I've drawn right here. This is the T by T matrix that tells us how similar is the thing at one location to a thing at another location. And the value matrix is basically like, if I say that my representation at this time step really only depends on the thing at this other time step, the value matrix tells you what is the actual representation that you're going to be pulling from that other time step that's going to replace your current representation. To be more specific about this, so xq is just your input here, x, times some d by d, or even a down projection to a lower dimension, but some transformation matrix, so it's just a linear transform. And then the same thing with xk, it's just another learned linear transform. And again, with xv, it's just another learned linear transform. So you just have three different projections of your input vectors. And you take, to get your attention matrix, you take the inner product of all pairs of what we can call the queries and the keys. And this gives us some matrix. And then we do a softmax to sort of normalize each row to sum to 1. So every time step basically gets assigned a distribution over all time steps in the sequence. And then when we do this matrix multiplication with the value matrix, what we're doing is we're doing a weighted sum over the value vector for every time step in the sequence, weighted by the softmax attention score for each of those time steps. And so, yeah, so when we do this final matrix multiplication to get A, the question was, can you say that sentence again? The answer is no, but I'll try to be similar because I don't remember what I said. Essentially what A is doing is for every time step, so the value of A1 is roughly just going to be a weighted sum over each xv, so that the projected version of each one of these vectors weighted by the attention score for each one of these time steps. So this self-attention matrix is this t by t thing, meaning for each time step in our length t sequence, we have a length t vector. And that vector is a probability distribution over all of the time steps. and we just do a weighted sum over their value vectors. And so just as an example, like if this is our self-attention matrix, literally like the number right here in the matrix is going to be like exp of the inner product of the third row of the query matrix and the second row of the key matrix over the sum of the exp of the third row of the query matrix and all of our keys. This is just the softmax, but I've just written it out for like a particular cell. Yes?
Learned weights in the entire model are just the W sub Q, W sub K, and W sub V matrices?
And the MLPs. Yeah, so after self-attention, we do another residual connection and normalization, and then we have an MLP that we apply. It's the same MLP for every time step. The weights are shared, but it's just sort of like a post-processing on the output of self-attention. But yeah, so now it's all the parameters. So it's the XQ, the WQ, the WK, the WV, and then this is a one hidden layer MLP, so we have two-way matrices here. And that's all the parameters, other than like your input embedding matrix, which is relatively few parameters. Yes?
Is there a benefit of learning WQ and WK separately since we're just multiplying them together?
Yeah, it's not obvious, but yes. Mathematically, it's equivalent. So actually, in an early version of this slide, I wrote it out with just the collapsed single matrix. Because like when you do the transpose of xk, right, we get x times WQ times WK transpose times x transpose. So you can just define a new matrix that's WQ, WK transpose, and it's like, it's the same, right? But it's not the same. Because when you train it, turns out it's like easier to train if you have both of the matrices. Because when you do one step of gradient descent, like you're going to update, well, we're getting in the weeds, but like each matrix is going to get like a rank 1 update. And if you have a product of two matrices, they both get a rank 1 update. So like the update you make to each of them, to the thing in aggregate is richer. So in some sense, it's like easier to optimize. It's not totally well understood. But yeah, people still do it with this like double matrix way because it just seems to work better. It's a good question though. Is there a question?
I was going to ask whether you have more matrices, but I guess you don't know. So
I don't know the answer to that. I think he was first, but I'll be too nice.
What do you mean by rank 1 update?
Now we're officially in the weeds, but I'm happy to talk.
I'll find out that. When we say we got multi-head attention, where does that show up in this book?
Yeah, good. So someone's paying attention at least. So this is not multi-head attention. This is single-headed attention. And so really what we'll do with multi-headed attention is we won't do this once. We'll actually repeat this. Basically, this WQ, WK, and WV matrices will all have an extra index, which will be the heads. And so you'll repeat this like 8 times in parallel. And each one of them will take like will project usually like a different subspace of X. Because
Maybe.
right, so like if you have like, yeah, basically one of the words in the sentence might be related to like, it might have multiple senses, for example. And so, you know, if you have the word bank, like maybe it's related to like river, because it's like a river bank, but maybe it's also related to like, you know, Federal Reserve, and like you haven't disambiguated what kind of bank it is yet, so you want to attend to both, but you want to do them separately. So you do them in the 2 different heads, and then later on you combine them. But yeah, that's sort of a detail of like real transformers that we'll omit for now. Okay, and so, oh yeah.
So is this normalization before or after the residual connection?
Usually after. Sorry.
What's the rationale behind this decision choice?
That's a great question. It's pretty much purely empirically decided, as far as I know. There are some papers that try to analyze some of these decisions and give rationales behind them. There's a paper I think called like Transformer Circuits, or a mathematical framework for transformer architectures, or something like this, from Anthropic, that gets into this in more detail, but my understanding is it's largely because it's what works best. But I'm not sure actually the location of the normalization makes a huge difference in the final performance. It's kind of arbitrary. Okay. Yes?
Sorry, I don't know if you explained this, but how exactly do the positional embeddings work? Are they, like how do you make them so that the transformer is order sensitive?
So it's literally, your embedding lookup gives you like a T by D sequence. So you have a sequence of length T, and you do your embedding lookup, and you get a D length vector for each time step. Your positional embeddings can literally just be like a stack of learned vectors, and like you have one for the thing at time step 0 and one for the thing at time step 1 and so on and so forth, and you actually just literally add them together. And that's what forms your input sequence, and you just learn them end to end. There are other ways of doing it that like aren't learned that also work, and there are more complicated ones that like try to make it easier to generalize to longer sequences than you saw during training. But like the basic idea is it's just like a vector you add to the raw inputs. All right. I'm going to move on. So the last question was your question, which was, remind me what your question was again.
How do you make the positional embeddings?
Right. Yeah. So the question was about the positional embeddings and where do they actually come from? And basically, it's just you have a learned vector for every time step in your sequence, and for each corresponding time step, you just look up the one at that index. There are more complicated ways of doing it, but yeah. Okay, so now we have the gray box, which is great because we love it. And we're pretty much done now, so we have lots of these blocks, and we train them all end to end, and we get some representation for every time step in our sequence. And then finally, if, for example, we're doing like masked pre-training, we just have a final linear transform that projects the representation at every time step into the dimensionality of our vocabulary. And then we do a softmax. This gives us a distribution over all the words in our vocabulary, and now we can just do like, maximum likelihood training or whatever. And this is pretty much the whole thing. Cool. All right, so we've talked about pre-training, we've talked about transformers. How do we actually fine-tune these guys once we have them pre-trained? So let's look at one more example. So here I've prepended this class token that we talked about before because it's not really needed to understand pre-training, but for fine-tuning, we're going to use it. So we're going to just push this sequence through our model, and when we do fine-tuning, oftentimes we'll just take the representation of the class token, and we'll fine-tune a new prediction head, which is often just a linear transform or a small MLP, on top of this class token representation. Okay, so that's pretty straightforward. It's pretty much what we said before. We were talking about regular autoencoders, but one of the big questions on hopefully on your mind is what do we do with this guy during fine-tuning? So I mean, we could freeze these parameters. We could fine-tune all of them. There are other options. Maybe we fine-tune some of them, or we could freeze them but inject some new parameters that we're going to fine-tune. And it turns out, in practice, people usually do sort of option 3 here. So in some sense, they kind of freeze and fine-tune them in lots and lots of different ways. And we're gonna look at one of these methods in a little more detail so that you have some intuition about what that actually means. And the method that we're going to look at, which again, there are many, and I don't mean to pick this one as like the end-all be-all, but I think it's reasonably concise to get your arms around, so I think it can be useful to work through. It's called low-rank adaptation of language models. And again, the intuition is like, we want to fine-tune our model a little bit in some sense. So we don't want to necessarily fine-tune all the parameters of our model because we don't want to destroy all of the knowledge in the model. And of course, there's the question of like, what does a little bit even mean? So I'm curious if people have just like a sense of, if we want to fine-tune our really big model, we want to fine-tune it kind of a little bit, just enough to learn the task, but not too much. Like, what would that mean to you in terms of maybe what a method might look like, or what we might want to avoid, what failure modes we might observe? Yeah.
Perhaps maybe you don't want it to lose the ability to do the original task, or like you don't want the whole probability distribution to change. You just want it
Right.
to be able to learn how to use this probability distribution.
Right. So, and in some sense, we want to preserve the original model, because if we totally throw away the original model, what's the point of starting from the pre-trained model? Yeah. Yeah, anything else?
I have a question. Actually.
Oh, sure.
So,
You want me to go back, or?
I can just ask. So basically, when you're just pre-training using masked language modeling, is it like the class token out of vocabulary for the fine-tuning, like for the downstream task, and how does it learn how to handle the class token?
Yeah, so the class token actually is in the vocabulary. It's just another usually it's like token 0 in the vocabulary, and it does show up during pre-training. For BERT, there's actually, I omitted one thing about BERT training, which is that we don't just do the masked language modeling. There's actually this extra task, this next sentence prediction task, where we take the representation of the class token and we just do binary classification, which is whether these two sentences are consecutive sentences or not. So like half the time you'll sample 2 random sentences from your data set, half the time there'll be one after another, and you just have to do this classification. And that's how we sort of train that representation. Yeah. But later work has shown that you actually don't need to do that. It doesn't really make a difference.
Tokens emitting somewhere, right? So what would you do?
Yeah, so as far as I know, the class token is just it's in the input during training, but it's not used. I don't think you mask it because it will always be the class token, so it'd be sort of degenerate. But you still get decent representations out of it. Yeah, so it's kind of mysterious. But there's a follow-up paper called Roberta, which is basically ablating some of the things in BERT, and turns out you don't need to do the next sentence prediction thing, and you can still fine-tune it fine. So if you're curious, you can look into that. Okay, this is going to take forever. Okay, we are here. Okay, so we talked about what a little bit might mean, and basically we've gotten to it, which in my mind is we want to preserve the knowledge in the pre-trained model. We don't want to totally obliterate everything that's there, and that's sort of like a learning-based objective. Practically speaking, we also want to avoid having to actually store a new copy of every single parameter of our model for every new task that we want to fine-tune on, right? Like a lot of these pre-trained models are very big. They have hundreds of millions, billions, or even hundreds of billions of parameters. It'd be really annoying if we need like a whole new copy of the model for every new task that we want to fine-tune on. So the other motivation here is like, we just don't want to have to add that much every single time from like a storage perspective. And so to get into this one method that addresses these issues, I want to take a brief walk back in time to 1972 to describe this sort of particular view on what a linear transformation actually does, which ultimately gets at this question of what is a little bit. So consider the fine linear transform, which is the building block of neural networks in general, but also transformers specifically. And we know that for some rank R matrix, which is a linear transform, we have a decomposition of this form. Using this decomposition, we know that if we evaluate the matrix vector product with some input, we can just rewrite it. So we can push the x inside the sum. And we have this essentially weighted sum of each vector v weighted by this inner product of x with this particular u sub r. So this is just like algebra, barely algebra at this point. And one way we can interpret this is that this matrix vector product wx is really outputting a sum over what we can think of as memories. So each VR is sort of like a memory, and each UR is kind of like a key that determines how relevant a particular input is to that memory. Right, so if x is totally irrelevant to a particular memory, VR, then that means x will be orthogonal to UR. And so this inner product will be 0, so we won't include that memory at all in our output. If x is very aligned with a particular UR, that means that memory is going to show up very strongly in our output. So this is not really even new math. This is just kind of another way of thinking about the linear transformation, which is useful for motivating all sorts of things in like computational neuroscience and ultimately machine learning. But it's useful here because now we can go back to what does it mean to fine-tune a little bit, and we can say, well, if a little bit means we just only want to add a couple of memories. And what that means is we ultimately just want to make a low-rank change to W. And that's convenient because a low-rank matrix can be stored much more effectively than the full-rank matrix. So we've kind of addressed both things here. We're going to preserve most of the knowledge because the new matrix is only going to differ from the original matrix by some low-rank change, and we can store this change very efficiently because a low-rank matrix is not a lot of parameters. And it's exactly what LoRa does. So when we do fine-tuning, ultimately we're going to start with some pre-trained parameters W0. These are frozen. And our fine-tuned parameters are just going to differ from our pre-trained parameters by some low-rank matrix AB transpose. So both A and B are these D by P matrices. So, sorry, I should have written W0 and WFT are D by D. So we're just assuming the matrix is square, but there's nothing specific to square matrices here. This works perfectly well for non-square matrices. And so when we compute this matrix product, we get some low-rank D by D matrix that we add to W0. and we fine-tune just A and B here. So we don't fine-tune W naught. And so we only end up needing to store kind of 2 times D times P new parameters instead of 2 times D squared new parameters for every layer. One minor note is that it's usually much easier to fine-tune these models if at the initialization we're starting out with the same function as the pre-trained model. So that means we want AB to be initialized with zeros. But the way we do that is a little bit tricky. So if we initialize both A and B as all zeros, we're actually not going to get any gradient for either of them, so we won't learn anything. And so if we want the product AB transpose to be zeros, but we want to be able to learn things, we actually need to initialize one of them as all zeros and the other with basically non-zero, like normal random initialization. So that's kind of a detail. You'll see that in homework 3, but it's something to keep in mind. So like I said, that's LoRa. I hope that was somewhat interesting to think through. But there are lots and lots of different methods for lightweight fine-tuning that people have come up with in the last few years. This is one sort of survey of a lot of them, which plots the percentage of the parameters of the original model that actually need to get updated with the actual accuracy. And we can see, at least for this evaluation, which is just one benchmark, LoRa is in the relatively like heavyweight in terms of these lightweight methods, but also the high-performing methods. But keep in mind, even though this is relatively heavyweight, it's still only fine-tuning less than 1% of the parameters of the model. And what's really interesting is that in the same paper, the paper has a nice, direct and audacious title like lightweight fine-tuning is better than in-context learning or something. But sort of their main result here is that actually this is the case, at least in some settings, where if you use some of these lightweight fine-tuning methods in the right way, you can get better few-shot performance than a GPT-3 model that's like 10 or 100 times bigger. And so in a sense, if you have sort of more than a couple of examples, in-context learning is still very powerful if you only have like one example to adapt on. But if you have a few more, if you have in the like 20 to 70 regime, which is I think what they studied in this paper, fine-tuning can be more parameter efficient or scale better than in-context learning. But again, this is very, very hot off the press, so to speak, so I don't want to make any claims that are too categorical. And you'll make a similar, slightly simpler, but similar comparison in homework 3, actually. Okay. How are we doing? We're doing great. Good for us. Last section. So we've talked about reconstruction as a heuristic for representation learning. We've talked about autoencoders, which are sort of the first stab at using this. And now we've talked about masked autoencoders, which sort of try to address some of the issues with them. And I want to talk about another related class of models, another sort of related kind of heuristic for pre-training, which is autoregressive models, which I believe you saw in a previous lecture on black box meta learning. But I want to revisit it in this context because I think it's interesting. So in a sense, autoregressive models are very closely related to masked autoencoders, but they sort of simplify a couple things. So first, we can think about what some of the downsides of masked autoencoders actually are. So, I mean, maybe the most obvious one is like we have this extra thing we have to pick. Like we have to decide how we're going to do the masking, and like maybe there are better and worse ways to do that, and it's not always obvious what they are, and so it just like causes us stress and we lose sleep and all sorts of things. There are other things like, as someone asked before, we're only masking out some of the examples. Sometimes it's 15%, sometimes it's 75%. Can we mask out more? Why not? Well, we're only using basically part of each example to train on. We're only using the parts that we masked out, and we're not computing a loss for all the other time steps. So in a sense, we're not like fully utilizing each training example. And then finally, the downside is that once we pre-train this thing, we can't actually sample from it. We don't have a generative model. We can't sample from the original, generate new samples from the new data distribution, which sometimes is interesting and fun. Okay, so basically the idea behind autoregressive models is we're going to simply ask, well, instead of masking out a random subset of the input, what if instead our sort of learning objective is just take a prefix of the input and predict the next word, or the next pixel, or the next token, or the next patch, or whatever. So now we don't have to pick a masking strategy at all. In a sense, we're masking every token. And so what we're going to learn is simply this autoregressive model, which parameterizes a distribution over the next token or the next word or whatever, given the preceding. So if we have, again, a training sequence like Joe Biden is the US president, we're going to actually convert this into 6 different training examples by masking out every word in the sequence and conditioning on the ones before it. So we don't really have this constraint of only using 15% of the example anymore because we're computing a loss on every single time step. And here I've added a beginning of sequence token because we need sort of something to put in the model to get our first prediction for what the first word is going to be. So one difference here is for mass language models, sort of the output at a particular time step is what we think that word is if it's masked. Here, the output at a particular time step is what we think the next word is going to be. So we have this like shift by 1 going on. So what this looks like when we actually stick it into our model is we have x naught, which is just the BOS token. So we put that in our autoregressive model, and this gives us some distribution over next tokens given just BOS. And then we look at the next token in the sequence, and this is used as both the input at the next stage as well as the target for the previous stage. So x1 is actually the target y0. And then we also put this combined sequence through our model. So now we have BOS and Joe, and we get a prediction over what we think the next token is going to be. And then we roll this out. So we see the next token, we see Biden. That's the target for the previous step. And it's also the sort of incremental input for this step, and we do this forever and ever. So this is great. We can do this, and you can write papers that people will talk about a lot, which is awesome. But I think I've sort of cheated a little bit here in terms of comparing autoregressive models to mass autoencoders. So I've said how, with mass autoencoders, we only mask out 15% of the example. We're not using the whole example here. We're masking out everything. That's great. But I've left something out. And you might be wondering, well, why can't we just do mass autoencoding but like use the same example multiple times until we've masked out everything, right? If we're masking out 20%, well, we'll just mask it out 5 different times. We'll use a different 20% every time, and now we've used the whole example. And that's totally true. We can do exactly that. But the difference is, for an autoregressive transformer, the representation that we compute for each prefix is independent of all the stuff that comes later. And the significance of that is we can actually do this sort of efficient training where we mask out everything really efficiently. And what I mean by that is we only have to compute a new representation for sort of the marginal new token at every time step. So when we're predicting what the first token is going to be, we have to compute a representation of BOS. But then when we're predicting the second token, we can actually just reuse the representation we computed of BOS, and we just have to compute the representation of the one new word that we're seeing, and so on and so forth. And so if we were doing this with a masked autoencoder, every time we change a single mask, since the attention is going both ways, the representation for every token depends on every other token in the sequence. If we change just one mask, we have to do a completely new forward pass of our model on the entire sequence. Whereas here, every time we add a new token, we only have to actually compute one new representation. And so this makes the fact that our sort of attention is only looking backwards makes it much more efficient to do this. So that's why we really are gaining something over just doing masked autoencoding with different masks.
Does that property make it hard to use these models for like spell checking or something like that, where you really would want to look in both directions?
Yeah. So one of the trade-offs that I think I'll mention in the summary is that the representation quality is a little bit worse for autoregressive models in general because you have a more constrained model. It can only look one direction. So you have some benefits, but you also have some drawbacks. Yeah.
This still uses the transformer architecture, right? So
right.
You have attention. So wouldn't the representation of the previous tokens change based on the attention from the?
Great question. Yeah. So the way we get around that actually is maybe easiest to visualize if we just look at this attention map I drew here. So basically, what's going to happen for the autoregressive transformer? Everything is the same, except what you end up doing is you literally zero out all of the attention scores that are on the upper half of the attention map. And so literally when you do this weighted sum, all of the terms in this softmax matrix, which would be the attention of a token to a token in the future, are manually set to 0. So they can't affect the output.
So the future, you can mask future tokens you're passing out by 0, like the tension weights will go to 0.
Yeah.
But I'm saying, you said that we can use cached representations from the previous semester, but because like when a new token is added and you're considering that new token, the tension value will change. The subsequent representation will also change for that particular token, right?
No, so the representation of a token at time t only depends on the tokens before t. So if I have in the autoregressive case, in the autoregressive case, when I compute the representation for Biden, this is only a function of the representations of Joe and BOS. So when I add is for my next training example, the representation of Biden is going to be the same because, again, it's only going to be a function of the words that come before it. So if I add words after it, they don't factor into the representation of Biden at all.
You try to change it because the meaning of the previous word would change based on the next word. So won't you try to change it, right? Or like when you add new tokens, you want to compute attention to the new token, like for the previous words as well.
So is the question that when I add a new word, is that going to change the representation of previous tokens?
Because we can compute attention for the new word and like change the like.
Yeah, so in a sense, this is a limitation. So the question is, when we add new words, don't we want the representation of prior words to change? Because like it's extra context. And in a sense, yes, we in a perfect model, we would be able to do that. But by making this simplification, we have some other benefits, which is that we can do this form of masking and reuse the representations. If we didn't have this constraint that the attention map, the map was masked in this way, we would have to do a complete new forward pass for every example. It would be much, much less efficient. And we also wouldn't be able to sample from the model because it wouldn't give us an actual autoregressive distribution that we can sample one token at a time and just condition on the past stuff. Yeah, one more, and then we'll move forward. I have a couple more slides.
So if the word that the model predicts as next is completely wrong, is that wrong representation still cached and used to predict future words?
Yeah, that's a good question. So during training, we do what we call teacher forcing. So we Oh, sorry, yeah. So if the model samples like a bad word, basically, like a random word, like Joe Biden dog, what's going to happen? During training, we don't use samples from the model. We sort of only use as input a prefix of our training data and just predict the next word. So we never actually use like a prediction of our model as part of the training process. But at sampling time, this can happen where basically like your model will, by some bad fortune, sample kind of a random or low probability word, and it'll get totally derailed, and it'll just start saying like dog, 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 and then like you just have to stop generating and try again.
So then what's the benefit of the cached representations if we already have the embeddings of all the vocabulary? So you can just directly map it, right?
Well, so the representation here of Biden is not just going to be of the word Biden, it's going to be Biden in the context of Joe. Yeah, so it's instance specific. So yeah, that's important. We're not just caching the representation of individual words, we're caching the representation of this prefix of the sequence in this specific context. So it's sort of caching within a single batch. And so just to hammer this home, autoregressive transformers are all over the place these days. So you have the whole GPT family, but you also have Megatron, which is a model from NVIDIA. You have OPT, which is sort of an open reproduction of GPT from some
Researchers at
Meta. Just because they were later doesn't mean we can laugh at them, okay?
No, it's just, it's like, it's not a solution.
We love being meta. And then there's other open efforts from, not from companies, from open source communities like GPT-Neo. And there are models for vision too that are autoregressive transformers for RL and for decision making, for navigating the web, and also for multimodal settings. For vision and language. So one case study of this is a model from DeepMind called Flamingo. And they're sort of getting at this question of like, how would you build a multimodal autoregressive model? And hopefully the answer is not from scratch. And that's what they sort of show in this paper. So for the most part, what we've been showing is fine-tuning as a form of specialization. So we take a general purpose model, we use few-shot data to make it a task-specific model. But in Flamingo, what they do is they use fine-tuning as a way to actually just combine two pre-trained models. So they have a pre-trained autoregressive language model and a pre-trained vision feature extractor, and they fine-tune with a little bit of multimodal data to get this autoregressive image language model. And I'm not going to go through the architecture because we're running a little low on time, but it looks kind of weird, but it's actually pretty straightforward. But what's really interesting about it is you do this autoregressive pre-training basically with unsupervised data scraped from the web of websites that have both images and text. And now you get a model that you can do few-shot prompting the way you can with GPT-3, but you can have images in the input too. So you can do sort of few-shot image captioning or visual question answering. And what's kind of cool is that actually the few-shot performance of the largest version of their model actually approaches state-of-the-art for models that are fine-tuned like on the whole training set. So that's pretty cool. One little note is just that our autoregressive model is actually different from masked autoencoders, and to skip right to the punchline, the answer is no. In a sense, an autoregressive model is really just a masked autoencoder with a specific form of the mask function, where we just, x is just a prefix of, x tilde is just a prefix of x, and y is just the next token. Okay, so just to summarize today, we talked about sort of the main intuition for autoencoders, which is that a good representation is one that lets us reconstruct the input. And we talked about masked autoencoders, which are a modification of this basic autoencoder that restores sort of a partially deleted input. And this helps avoid some of the degeneracies of unmasked autoencoders. These masked autoencoders are state-of-the-art in pre-training in few-shot learning for both vision and language. And we saw autoregressive models, which are really a special case of masked autoencoders. A couple pros and cons of contrastive models and autoencoders and masked autoencoders. I don't know if I need to really enumerate these because I guess we're right about out of time, but I think the main trade-off that you can think about is that especially using some of these new contrastive learning methods that don't require sampling negatives anymore, really one of the biggest trade-offs is that the contrastive models learn really high-quality representations, but the masked autoencoders might be a little better if you're actually going to fine-tune the model. So if you just want to compute representations and like pre-cache all the representations and then throw away the model, maybe the contrastive model will work a little better. But if you want to keep your actual pre-trained model around and fine-tune it a bit, the masked autoencoders might work better.